This problem says prove that the limit as x approaches -3 of 2x plus 1 equals -5. Before we prove this, let's go over the definition of a given case where you say the limit as x approaches some a of some function f of x equals some value L. And what this is a predicate logic where you're saying for all values of some epsilon, which is greater than 0, for all positive values of an epsilon, there exists or there is a value of delta which is greater than 0, such that this in the parentheses is true. And what's in the parentheses is an implication, which means if this part is true, then this part is true. And what is the condition? We're saying if the absolute value of x minus a, which if you remember from absolute values, if the distance between a given x and a is greater than 0 or less than delta, then the distance between f of x and L is less than epsilon. Now let's talk about this in informal terms that hopefully express the meaning. You see, L is the value of the limit, except possibly right at a. Sometimes the value at a is f of a, but just in the special case that it's not, I drew it as a hole in the function or an exclusion. But this isn't always the case. It could be defined right at a, but it doesn't need to be for the definition that we set of the limit. We're saying that we can always make this epsilon as small as we want. We can always make the, you can call it the tolerance, as close as we want to L. For any value of epsilon that is positive, however small, there will be a value of delta, so that if the distance between x and a is within this box, then the value of the function will be within this range. So if you haven't seen this before, and definitely if you haven't studied predicate logic, it's good to study that for a while. And this sometimes can take a while to get. But once we have that, how do we use it to prove that this case is true? How do we prove that? We're saying for all positive values of epsilon. So we start with any arbitrary value of epsilon. So we're going to say that the distance between the absolute value, the distance between 2x plus 1 and -5 is less than some value of epsilon. We start with that. Here's the function, and here's the value, L in this case. Why do we start with the conclusion? Because we're saying for any value of epsilon, we want to go backward and see if there's a value of delta, such that if the value is within delta of -3, then the value of 2x plus 1 is within epsilon of -5. Okay, and the way we're going to do that is we're going to perform manipulations on this absolute value. We can see that minus negative is the same as 2x plus, what is 1 minus negative 5? Is 1 plus 5 is 6, is less than epsilon. Okay, 2x plus 6 is less than epsilon. Now we need to use another property of absolute values. Can we factor out? We can factor it out right here. We can factor a 2 out of 2x plus 6. This is x plus 3 is less than epsilon, right? What does this property of epsilon mean? What does this property of absolute values mean? You see, if you have the absolute value of a product, it's equal to the product of the absolute values. So we can do that. What do we have here? Let me put the parentheses. We have 2 times x plus 3. So we can make this 2 times x plus 3 is less than epsilon. What's the absolute value of 2? It's just 2, right? Okay, I'm going to rewrite to save some space. 2 times the absolute value of x plus 3 Now we have an inequality expression. 2 times the absolute value of x plus 3 is less than epsilon. We can divide both sides by what to get this all by itself? 2. So we can, and 2 is a positive number, so the inequality does not change directions. So the absolute value of x plus 3 is less than epsilon divided by 2. Now, x plus 3, you can look at what we're trying to shoot for. We're trying to shoot for the distance between x and negative 3. So x plus 3 is equivalent to x minus negative 3, right? Is less than epsilon over 2. So look at this right here. And we're saying we can add on, and we can add the constraint that we don't want to worry about the limit right at negative 3. We're saying, obviously we can tell with this particular function it does exist at negative 3, but we can do this because we don't care about the value of the limit at negative 3. And we're saying that the absolute value of x minus negative 3 is less than epsilon over 2. So we say, let delta be of positive value that equals epsilon over 2. Then, obviously, it's greater than 0, and we're saying that we have found that because we started with the assumption that f of x minus negative 5 was less than epsilon, and we came to the conclusion that delta exists, now we can say that if x is within this delta of negative 3, then 2x plus 1 will be within epsilon of negative 5. So that means that we've proven that the limit as x approaches -3 of 2x plus 1 is -5. So how do we do that? How do we do this problem? We started out by assuming that the absolute value of this function minus the value that we're supposed to prove is the limit is less than some epsilon. And then we used algebraic techniques to prove that if we start with that, then x, the absolute value of x minus this is less than some delta, which will be in the form of a function of epsilon. So that was the technique, and we proved it. This problem says illustrate graphically that the limit as x approaches a of the function x squared is equal to a squared. So this problem is not a analytic proof. It just wants you to strengthen your grasp of the concept by showing a picture of it. So let's do this. Let's draw a bit of a coordinate axis system, and A, here's the x-axis right here. Here's A. We know what the function x squared looks like. It's a parabola, and it looks like this. We're just drawing a bit of a function, and we're saying that when x is equal to a, we know that the value of the function x squared is going to be a squared. So far we've just drawn the function. How do we graphically talk about the limit having a value? Remember what the limit is? Let me draw something over here. If we're saying that the limit of a function is L is some value, and we're saying that we can place bounds above and below L with a small positive number, an arbitrarily small positive number, epsilon. So what would this value be? If L is here and epsilon is a positive value, this would be L plus epsilon. This would be L minus epsilon. Well, in this case, let's say we drew some horizontal lines. Let's just assume that these are equal. Just ignore graphics. This distance here is epsilon. Just pretend that this distance is also epsilon. Then this value would be a squared plus epsilon. And this value would be a squared minus epsilon. We're just drawing what the limit means. And remember, with the definition of the limit, we're saying that the function may look like this for some general function. We're saying that for any epsilon that we choose, no matter how close to L, except possibly right at A, we're saying that there will be a value of delta, what would this be? This would be a minus delta. And what would this be? A plus delta. And what is the closest that we can get? What is the farthest away that we can get from this value A and still stay within the horizontal boundaries? Maybe it's this one. And now with delta, since we chose the same value, we want to stay, this is A minus delta. Then if we go the same distance right here, we say this is A plus delta. You see how if we stay within delta of A, then we will stay within epsilon of A squared. So that would be a graphical showing of the limit as x approaches A of x squared being equal to A squared. This problem says prove that the limit as x approaches 6 of 9 minus x over 6 equals 8. And so we say that f of x minus L is less than epsilon. We start out that way. So we say that 9 minus x over 6 minus 8 is less than some epsilon. Okay? Now, we have to get from here to having something x minus something is less than some delta, where this delta is in a function of epsilon. So that's where we're headed right now. So how do we do this? We start out by what's 9 minus x over 6 minus 8? What can we do here? We got 9 minus 8. We can move that over. So we can say 1 minus x over 6 is less than some epsilon. What would you do next? Can we combine these to have a single fraction? In that case, 6/6 is 1 minus x over 6 is less than epsilon. Now that they have the same denominator, we can say 6 minus x over 6 is less than epsilon. Okay. What can we factor out of this? You remember the property of absolute values, where you say the absolute value of AB is equal to the absolute value of A times the absolute value of B? Think about how you could use that. Can we rewrite this fraction 6 minus x over 6 as 1/6 times 6 minus x is less than epsilon? Yeah, this is the same as this. And now, what can we rewrite this as? let's say that A is 1/6 and B is 6 minus x. Then we have this. Well, what's the absolute value of 1/6? It's just 1/6, right? Okay. We can multiply both sides by what to get this all by itself? We can multiply both sides by 6. Then 6 minus x is less than 6 epsilon. Is this the form that we need just yet? It's close, but not quite. What will we do next? What do you think should be done next? What is the target form? Then some delta, which is what do we know about absolute values? Is this true? The same thing. Can we change the... This is true, isn't it? So can we write this? If 6 minus x is less, if the absolute value of 6 minus x is less than 6 epsilon, then can we say this? If this is true, then this is true, right? Then this is what the form that we want. Now we say let delta be the same thing as 6 epsilon. And also we add the constraint that we say that delta is greater than 0, because we don't accept the situation where x is right at 6. Okay? This is good because this means that for any given epsilon, we're saying that if x is within delta of 6, where delta is defined as 6 epsilon, then 9 minus x over 6 is within epsilon of 8. Here's a problem that says find an example of a function f of x that is defined at a, at some value a, and the limit as x approaches a of f of x exists, but the limit as x approaches a of f of x does not equal f of a. There's a lot of words in there. Reread it a couple times if you want to get what it's talking about. And I recommend you draw a picture as you think about some function that you come up with. Here's one that I came up with. Let's say this is the coordinate axis. There's x, and this is f of x. Well, this is y, the y-axis. Now, let's say that this value a is right here. Actually, let me put it over here. I'll show you let's say that a on the y-axis is right here. What about the function what does the function f of x look like? I haven't completed yet, but I'm just setting up a example. You know, f of 1 is 1, f of 2 is 2. It's going to be a line where every x value and y value are equal. In that case, when x is a, y is a. Now don't worry, I'm not done yet, but what if I made this instead a piecewise function where f of x is x for all values x is not equal to a, and what if at this point a, when x is equal to a, then the function is equal to so look at this function. It's equal to x for all values of x except for a, but when x equals a, the function is equal to x plus 1. That means that at a, the function's value would not be a. It would suddenly, for that one value, be a plus 1. I mean, you could get so close to a within a billionth of a unit, and the value would still be within a billionth of a, but when it is exactly a, suddenly it's over here. Do you remember the definition of the limit? How with the limit, you're supposed to be able to come up with an epsilon as small as you want, or as close to the value of the function as you want. We'll call this a plus epsilon right here, and this is a minus epsilon. And with that value of epsilon, you're saying there exists a delta such that this is a plus delta, and this value is a minus delta. So this function, you can get as close as you want. You can set as small a tolerance as you want, and there will be a delta, not including a itself, but there will be a positive value of delta, saying that when you're close, within this closeness of a, then f of x will be within epsilon of a. So this function is defined at a. This is its value at a. And the limit exists because you can get as close as you want to a. But if you're talking about right at a, the function is not equal to a. It's equal to a plus 1. You could come up with lots of examples, but that's the one that I came up with. This problem says show that the limit as x approaches 2 of x plus 2 over the absolute value of x plus 2 does not exist. So this is a proof of non-existence problem. How would you prove that something doesn't exist? Do you have any thoughts? Let's go back to the definition of the limit. Well, if a function does have a limit, let's say the limit as x approaches c of f of x being equal to L means, this is a definition, we're saying this is what it means. It means that for all or for any epsilon greater than 0, however small, there exists a delta greater than 0 such that if the absolute value of f of x minus L is less than epsilon, what does this mean? This means that the distance between f of x and L is less than epsilon. As long as the distance between f of x and L is less than epsilon, then the distance between x and c is less than delta. And if you want to exclude the value right at c, you can put this. We're saying that the distance is positive and it's less than delta. So graphically, we're saying that if this is the function, and this right here is c, if we specify any epsilon, then there will be a value delta such that if we're in here, then the value of the function will be within here. So going back to this function, let's take a look at what this function looks like. Let's draw it. Before we draw, let's think. X plus 2 divided by the absolute value of x plus 2. If this is a positive value, then x is greater than negative 2. And this is always a positive value of the same magnitude. So that means that whenever x is greater than negative 2, this would be a positive 1. Because if, say, x is 0, 0 plus 2 is 2. 0 plus 2 is 2. 2 over 2 is 1. Now, if x is less than negative 2, for instance, say negative 3, negative 3 plus 2 is going to be negative 1. Negative 3 plus 2 is negative 1. The absolute value of negative 1 is 1. So this is negative 1. So this is what this function looks like. And we're talking about this right here. Let's say that we chose an epsilon. We're supposed to be able to take any value of epsilon. Let's say we take an epsilon value of 1/2. Let's take a value of, say, 1/3. Because if we can take a value however small, we should be able to take a value of 1/3. Let's see. Let's say that we choose the value 1/3, and first of all, if -2 is the value that we're talking about, are these two, whether we're coming at it from the negative direction or we're coming at it from the positive direction, is there a value of delta so that as long as we're within delta of -2? No, so we've already found a counterexample. We are saying that looking at this function and giving some test values, there is not a value. So we're saying for all x, for all epsilon, this is the symbol, there does not exist a delta such that if x plus 2 over the absolute value of x plus 2 minus anything, there's no L such that for all epsilon so what I meant to make was there is no L such that for all epsilon there is a delta such that the absolute value of x minus L means that x minus 2 is less than delta. So if there is no value that you can get closer and closer to, then it does not exist.